Hello and welcome. This is a continuation or precedence to a video I made once. I just wanted to kind of make things clear. So we all know the Lorentz force, right? Force is equal to the E field plus the charge times the velocity crossed at the B field, right? The Lorentz force. All right, but what if we divide it by volume? Similarly like taking the conservation of energy equation divided by volume, you get the Bernoulli equation, right? Well, we're going to get something close like that, but it's going to be something entirely different, similar to that analogy. So divide everything by volume, basically, and we have a change in force with respect to volume, right? Is equal to the charge density times the E field plus the current density crossed with the B field. All right. So what does that mean? We don't actually, I don't know how we can get numbers for charge density or our current density. So let's put this into something that we can actually get in values for, we can actually measure and calculate. So by Gauss's law, charge density is equal to the permittivity of free space times the gradient of the E field. Okay, permittivity of free space times the E field times the gradient of the E field. By Ampere's law, we're going to use these pieces and parts. We'll be replacing that. I'll make it a little bit easier to follow here in just a moment. But by Ampere's law, the curl of the B field is equal to the current density times the permeability of free space plus the permittivity of free space times the change of the E field respect to time times the permeability of free space. So still something that it's a little bit difficult to work with still, but it's getting easier. Okay, getting a little bit easier. So by Ampere's law, J is equal to the curl of B minus the change of E with respect to time. All right. So now, if we put that into here, if we put that into there, we'll end up crossing the change of the E field with respect to time with the B field. And we can express that, we can expand that out to say this statement right here, the change of the cross of the E and B field with respect to time. We've seen that before with the pointing vector. All right, so the permeability of free space times the pointing vector is equal to the electric field crossed with the B field. Okay, electric field crossed with the B field. So we're going to turn that into the pointing vector right there. All right, it'll go right here. This stuff right here is right there. Okay. Now, if you didn't know by Faraday's law, the change of the B field with respect to time is equal to the curl of the E field. So we're actually going to replace this thing right here with the Faraday's law statement. Okay, so the curl of E times the cross product of, or with the cross product of E, not times, but just with the cross product of E. So what does all that mean? And let's make it a little bit simpler, shall we? So here's what we started out with up top. Well, it's not the first thing we started out with. This is the divide after we introduced volume, the change of volume. Okay, after we introduced that, this is what we had, the Lorentz force using volume. And so when we take a step down, we'll see that by Gauss's law, we replaced charge density. Okay, by Ampere's law, we replaced J with this stuff. Okay, by Ampere's law, we replaced the current density with all this. All right, still crossing it with B. Okay. Now, taking it a step further, the change of the force with respect to volume, derivative force with respect to volume, is equal to, here we have the Gauss's law again, times the E field, minus now the curl of B cross B, all right? There's a minus sign in there because of the manipulation of Ampere's law, okay? We had to do that to account for introducing Ampere's law into this. So now, here we have our permittivity of free space times, and now we're replacing all this with what we're going to have going on right here, okay? The change of the cross of E and B field with respect to time minus the taking out rather the E field, the crossing with the change of the B field with respect to time. Okay. So taking it another step down, we still have our Gauss's law times the E field minus our curl with B cross B. This time we took the permeability of free space out because it's just a constant. We can just take that thing out. Minus, now we still have the permittivity of free space times all this inside these bracketed set of parentheses. We've replaced E cross B with the Poynting vector, and now we're adding the I'm sorry, because we also took out our subtraction sign out here on the outside. We are adding our E field crossing with the curl of the E field. And so this is our final expression. However, it's easier to read on the next step down. Okay, easier to read down here. Combining all fields together where they're supposed to be. Okay, combining all things where they're supposed to be. All right, thank you very much. And that's set up for Maxwell Tensor.